Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the class on pericyclic reactions. Today we will be discussing yet another interesting part of the sigmatropic rearrangements, that is 3,3 sigmatropic rearrangement reactions. See, so far we have thoroughly discussed and tried to understand about the 1,3 sigmatropic rearrangement reactions as well as the 1,5 rearrangement reactions. If you clearly observe those reactions as discussed in the first class itself during the classification of the sigmatropic rearrangements, so we have seen there are two different types of sigmatropic rearrangements which depends upon the position. So they are 1, J type and I, J type of sigmatropic reactions. In the case of 1, J type of sigmatropic rearrangement reactions, if you see this is the sigma bond and the termini of the sigma bond is holding the atoms or groups, right? So on one part, so it is changing the position, on the other end it is not changing the position. It is intact with that particular atom or group. So those type of sigmatropic rearrangements are classified as 1, J type of sigmatropic rearrangement reactions, where one position is held constant, so other position is only changing, other end of the sigma bond is only changing. Whereas in the second case, I, J type of sigmatropic rearrangement reactions, this particular sigma bond which is migrating from the origin to the termini, so will be able to change both the ends on the sigma bond. So these type of sigmatropic rearrangements are all categorized as I, J type of sigmatropic rearrangement reactions. So 3,3 sigmatropic rearrangements belong to the I, J type of sigmatropic rearrangement reactions. So what is happening here is the sigma bond which is initially between 1 and 1 position is now entirely shifting to a new location where it is connected now to the 3 and 3 positions. So the best example for the sigmatropic kind of reactions is 1, 5 hexadienes, as well as allyl vinyl ethers or allyl phenyl ethers, right? So these molecules are the basic examples for the determination of, for the understanding of sigmatropic rearrangements which involve 3,3 migration. Okay, so 3, 3 sigmatropic rearrangement reactions are again divided into two types. One is Cope rearrangement and the other is Claisen rearrangement. So of course both of them would involve in the 3, 3 sigmatropic rearrangement, but depending upon the type of this molecule involved in the rearrangement, so they are categorized as two different types. One is Cope type of rearrangement and the other is the Claisen type of rearrangement. Okay, so in Cope rearrangement you can see the involvement of a 1, 5 hexadiene. So this is the 1, 5 hexadiene which participates in the 3, 3 sigmatropic rearrangement reaction. Whereas in the case of Claisen, the involvement of an allyl vinyl ether is seen. So this part is vinylic part and this part is the allylic part. So allyl vinyl ether, which involves in the 3,3 sigmatropic rearrangement, is studied under Claisen type of rearrangement. So the other example is this one, which is allyl phenyl ether. So this is the phenyl group and this is the allyl group. So these type of molecules with different kinds of substituents are capable of involving in the 3,3 sigmatropic rearrangement reactions, right? So we all know very well and well aware of the numbering on the sigmatropic substrates, right? So the sigma bond which is intended to change the position should be given the preference. The carbon, saturated carbon atom which is attached to it should be given the preference, and we with help of Woodward-Hoffmann rule, we assume like, so the sigma bond which is subjected to migration is undergoing homolysis, right? So numbering should be given from here this way. This is a separate part now, and 1, 2, 3. So now clearly it is evident from this, like the sigma bond which is earlier in between 1 and 1 position is likely to change its position to 3 and 3, right? So how it is happening means, this is migrating here and this is going back here. So the resultant product will be like this. So 1, 2, 3, 1, 2, 3. So the new sigma bond is now seen in between 3 and 3 position. So such a type of rearrangement reactions would happen under thermal conditions between 250 to 300 degrees centigrade. So this type of 3,3 cope rearrangements will happen to see in between 250 to 300 degrees centigrade with an activation energy of approximately 35 kilocalories per mole. The beauty of this thing is, if you try to substitute some groups on these 2 carbon atoms, then depending upon the nature of the groups substituted, the activation energy may further decrease. And the basic example, basic reaction, this one is also treated as degenerate sigmatropic rearrangement reaction. Degenerate, that means from this molecule to this molecule, whatever the energy required is same, as well as the energy of this molecule is absolutely equal to the energy of this molecule, right? So there is no difference here and there. So that is why such type of reactions are called as degenerate rearrangement reactions. Now if you include a substituent, then the things will change. Then no more you can call it as a degenerate rearrangement reaction. So if 2 phenyl groups are there, for example, and now you can see the phenyl groups like this, right? So now the activation energy, because of the involvement of the phenyl groups, it lies in between 20 to 30 kilocalories per mole. Means depending upon the nature of the substituent attached to this particular type of molecules, so the activation energy may be varied, it can be decreased. Yeah. So now if the same molecule is having an NH group at this position 1, 1. So this scope rearrangement will be now called as Aja-Cope rearrangement reaction. Because nitrogen is involved, we call it as Aja-Cope reaction. So the product will be this one. If in such kind of molecules there is an OH function, so this is also exactly similar to the normal Cope rearrangement, but only difference is the involvement of a OH group at this position. So now these type of reactions are called as oxy-cope rearrangement reactions. So what will be the product? This one, or it can, this is the enolic form, so it can be also seen like this, keto form. Okay, so these are the different varieties of the cope rearrangement reaction which we will be examining or trying to understand in the classes. So now it's time to also look into the analysis of the 3,3 sigmatropic rearrangement reactions, because in the beginning we came to know that the orbital correlation method is not that suitable enough to analyze the 1,3 sigmatropic rearrangements or 1,5 sigmatropic rearrangements, or in general many of the sigmatropic rearrangement reactions. So we have taken the help from the frontier molecular orbital approach method, so to understand or to analyze the sigmatropic rearrangements under thermal conditions as well as under photochemical conditions. So the same will be done here. So we'll try to use the frontier molecular orbital theory to understand or to analyze the 3,3 sigmatropic rearrangement reactions now. So as seen in the example 1,5 hexadiene. So as per Woodward and Hoffman, we need to assume that the migrating sigma bond is undergoing a homolysis. Therefore, in this particular type of sigmatropic rearrangement reactions, you will be always able to see two radical systems, two allyl radical systems. This becomes one allyl radical and this becomes one more allyl radical. So two allyl radical systems will be seen. As we already understood, like all thermal reactions are ground state reactions and all the photochemical reactions are first excited state reactions. So we will try to see each one by one. So thermal reactions, under thermal conditions, what is going to happen? So under thermal conditions, you have to consider both the allyl systems, allyl radical systems, and the reaction happens in the ground state only. The reaction is happening under ground state only. So therefore, the electronic configuration or the molecular orbitals, whatever you can be able to see for an allyl system or a 3-carbon system is like this: Psi1, Psi2 and Psi3, right? So which becomes the HOMO now? As said, so under thermal conditions, the reaction will happen in the ground state only. So HOMO should also be selected from the ground state here. So Psi2 becomes the HOMO under ground state conditions. So the one more important thing you need to notice here is we have to select HOMO molecular orbital only in both the allyl systems. So we need not to consider any LUMO molecular orbital, right? So HOMO should be selected from both the partners. So what are the partners? Two allyl radical systems are the partners, and in both the cases you have to choose the HOMO molecular orbital only. So how would it look like? How would it look like? Psi2 molecular orbital means, so this is the node and this one. So Psi2 molecular orbital, right? So even number molecular orbital. So obviously there is a difference in the wave function on the lobes in the same phase. So this is the lower phase and this is the upper phase, right? So one more allylic system is there this way, and for it also Psi2 becomes the HOMO. Therefore this is the case, right? So let us say the blue color defines the positive wave function, positive lobe, and the pink color or purple color, pink color defines the negative wave function. So the blue color represents the positive wave function and this represents the negative wave function. So sigmatropic rearrangements need to see two types of approach, two modes of approach. One is the suprafacial mode and the other is the anterofacial mode. If this is the pi system, if the sigma bond is breaking at this phase, lower phase, and then making the bond at the lower phase itself, we treat it as suprafacial mode of shifting. So if it has to cross the pi system, then we treat it as the anterofacial mode of shifting. So now first we will see the suprafacial mode of shifting, migration, 3,3 migration. So initially there is a bond between these two lobes and now it is slowly breaking down and then it is making up the sigma bond over here. You can see the positive lobes are involved in the sigma bond formation earlier. Now this is breaking. So now the lobes of same wave function are involving in the making of a new sigma bond at this termini, right? So therefore it is completely allowed when the first individual is a supra partner as well as the second individual is also a supra partner. So what we can conclude here with this thing is supra mode of 3,3 sigmatropic rearrangement reactions under thermal conditions is allowed, symmetrically allowed, right? So now quickly you look into the other modes also. So this is plus and this is minus. Yeah, plus and minus. Yeah. Now what are the other possibilities we need to check is supra antera, antera supra and antera antera mode of rearrangement reactions. Now if the first partner is supra, that means it is using the lobes from the same phase. So this is the lower the lobe on the lower phase and this is also lobe on the lower phase. If both are involved in the bond formation, it acts as a supra partner. And now if it has to be an antera partner, what should happen? A lobe from the upper phase and another lobe from the lower phase should be involved, right? So if it is an antera partner. Now supra partner indicates like this is the existing sigma bond previously. Now it is trying to break down and involve in the bond formation by antera mode. You can see now if the second partner is antera partner, what it is happening? So the negative wave function is likely to combine with the positive wave function, which does not result in the bond formation. So it is symmetrically not allowed. And the other option is antera supra, plus minus plus minus. Right. So now the first partner is antera partner and the second partner may be supra partner. So what is going to happen? So now this is an antera partner, therefore one of the lobe from the lower phase and the other lobe from the upper phase is involved in the bond formation. So which indicates like, see, the positive lobe is connecting with the negative lobe of the second partner. So it does not result in the formation of a bond. So therefore antera supra mode of 3,3 sigmatropic rearrangement under thermal conditions is also forbidden. So what else we can see is antera and antera partners. So now the first partner is antera and the second partner is also antera. So you see now the first partner has used one of the lobe from the lower phase and one of the lobe from the upper phase. Whereas the second partner also using one of the lobe from the upper phase and the other lobe from the lower phase, which clearly indicates like it is going to result in the bonding mode of approach. So now antera as well as antara mode of 3,3 sigmatropic rearrangement is also allowed. So what is allowed here? Supra mode of interaction under thermal conditions. This is happening under thermal conditions is allowed, as well as antara mode of interaction under thermal condition is also allowed. So under photochemical conditions, so the analysis will be like this. See, photochemical conditions of 3,3 sigmatropic rearrangement. So there will be 3 molecular orbitals, Psi1, Psi2 and Psi3 for each species, reactive species, right? So 2, as per the assumption, after the homolysis, we will be getting 2 allyl radical systems. So for each one, we will see here now like Psi2, and because all the photochemical reactions happen under the first excited state. So for one partner, we have to choose the HOMO from the first excited state. So for first partner, the HOMO should be selected from the first excited state. For the second partner, the HOMO should be selected from the ground state only. So therefore, here also we have to consider only the homomolecular orbitals but not the LUMO. So whereas in the thermal conditions, we have choose the homomolecular orbitals from each partner under the ground state conditions only. Whereas in the photochemical conditions, the HOMO should be selected for one partner in the first excited state and for the other partner in the ground state. So therefore, for the first partner, Psi3 becomes the HOMO. For the second partner, Psi2 becomes the HOMO. So how does these molecular orbitals look like? So Psi3, which is HOMO for the first partner, is an odd molecular orbital. So wave functions will be same. Psi2 will be HOMO for the other one. Right, this is the Psi2. So opposite wave functions will be seen. So if you see this and the modes of interaction, if we try on this molecular orbitals, we come to know like if the first partner is supra and the second partner is also supra. So supra mode of interaction is forbidden under photochemical conditions. Is forbidden under photochemical conditions. Supra mode of 3,3 sigmatropic rearrangement under photochemical condition is symmetry forbidden. Whereas if you look into the supra antara or antara supra type of interactions, plus minus plus, this is Psi2 again, Psi3. So plus minus. So here you will get 2 nodes and here you will get 1 node, right? So now the possible combinations or modes of interaction is one partner being supra, the first partner, the second partner being antara. So what is going to happen? See, if it is supra, both the lobes should be from the same face, either the lower face or from the upper face. So this is supra, so I am considering both the lobes of this particular individual from the lower face. So this is going to give a bonding interaction. Now this is an antara partner, so already we have connected it via the upper face lobe here. So therefore obviously because it is an antara partner, the lower face lobe should be chosen. So now you see the wave functions are same here and here. So this is bonding interaction. This is bonding interaction, which indicates like under photochemical condition, for a 3,3 sigmatropic rearrangement, that is the cope rearrangement. So when you choose the homomolecular orbital for the first partner in the first excited state and homomolecular for the second partner in the ground state, you can observe like supra-antara mode of interaction is allowed. Similarly, antara-supra interaction is also allowed. So how would it look like? Plus S. Right. So now the first partner is antara partner and the second partner will be supra partner. So first of all, the first partner has used one of the lobe from here. So as this is an antara partner, choose the lobe from the other face, opposite face, right? So one lobe from the lower face and one lobe from the upper face is involved now. So this becomes an antara partner, right? So now this being a supra partner is using the lobes from the same face. So this is also allowed, and this particular interaction is going to give you bonding interaction, right? So the last one is antara mode of interaction, which would also be forbidden, similar to supra mode of interaction, right? So now we can conclude saying that the Woodward-Hoffmann selection rules will be like this for 3,3 sigmatropic rearrangement reactions. So for a thermal condition, 3,3 sigmatropic rearrangements are allowed supra mode, in supra mode. So under photochemical conditions, the 3,3 sigmatropic rearrangements are allowed in the supra-antara mode or antara-supra mode of interaction. Let's quickly have a table, and before that try to see the molecular orbitals of the same, right? So this is the Psi2 molecular orbital, isn't it? You can see Psi2 molecular orbital. So positive wave function and negative wave function are there in the same phase at the terminal carbons. So and now this is a Psi3 molecular orbital. This is a Psi3 molecular orbital where you can see the same wave function on the terminal carbon lobes. Now you look at these things. Now if these two are interacting for a 3,3 sigmatropic rearrangement, right? So when it is going to happen? Under photochemical conditions. So one, you have chosen the HOMO, that is Psi3 molecular orbital. This is Psi3 molecular orbital. The other HOMO is in the ground state, which is Psi2 molecular orbital. So the interaction between these two will be like this. So one side it is obviously giving a bonding interaction. The other side, the lobes are with different wave functions, so it is not possible. What should happen now? Antara mode. One of the partners should become antara mode. So therefore the bonding will be possible. Okay. So in thermal conditions, the situation is different, like this. You can see here, like this. So under thermal conditions, both the HOMOs are from the ground state only. So this will be like this. This is Psi2 ground state and this is Psi2 under ground state HOMO. So for thermal conditions. So both gives the bonding interactions. So therefore it is thermally allowed reaction. So mode of interaction or shifting allowed or forbidden. This is a conclusive table for the 3,3 sigmatropic rearrangement Woodward-Hoffmann selection rules. So if both the under thermal conditions, let this be under thermal conditions. If both the partners are supra, so thermally it is allowed and photochemically it is forbidden. if one of the partner is supra and the other is antara, so therefore it is photochemically allowed and thermally forbidden. If the first partner is an antara partner and the second one is a supra partner, so then again it is photochemically allowed but thermally forbidden. The final one, mode of interaction, if both are antara partners, then again it is thermally allowed but photochemically forbidden. So as we have now discussed, like 3,3 sigmatropic rearrangement reactions are supra-supra allowed or antara-antara allowed under thermal conditions. We call these reactions as thermal reactions. So if you remember properly, so in the Diels-Alder reaction, which is a cycloaddition reaction, so Diels-Alder reactions are also thermal reactions where supra-supra interactions are allowed under thermal conditions. So similarly, Cope rearrangement is a thermal rearrangement reaction. So we can work out the stereochemical aspects, because in this molecule, whenever there are substituents at these positions, will offer us so much of stereochemical parameters to be discussed. If you see in the molecular model case, so this is the 1,5 diene. So this is the first carbon atom when you are giving the nomenclature as per the IUPAC. 1, 2, 3, 4, 5 and 6. 6 carbon atoms are there, hexa, 2 double bonds are there, diene. So diene position is 1 and 5, right? So when you are coming for the sigmatropic rearrangement reactions, now what we need to consider here is the sigma bond which is breaking and then migrating. So this is the sigma bond which is breaking now, right? So you have to take this saturated carbon atom and give the numbering from here. This becomes 1, 2, 3. And the sigma bond is connected on the other end with another saturated carbon atom, 1, 2, 3. So therefore 1, 2, 3 and 1, 2, 3. Two allylic systems are getting generated if you assume like this sigma bond is undergoing homolysis, right? So after reaction, what is happening means this pi bond is moving here, this sigma bond is moving here, and this pi bond is converted into a new sigma bond here, right? Therefore, you look this molecule like, so after sigmatropic rearrangement, so what happens to the molecule is, you see the molecule in this way, you can see now, right? So double bonds will vanish from here and then they appear here in between these two carbon atoms, and now this becomes the thing. So this is the reactant molecule. Like this, right? So this is moving here, coming here and going here. So whatever the substituents are there here, right? So this is what going to happen when the molecule undergoes sigmatropic rearrangement. So this is the Psi2 molecular orbital under thermal conditions, and so this is the Psi2 molecular orbital for the another allylic system under thermal conditions. You can see the suprafacial interaction is allowed here. So the positive wave functions previously in bonding, they may break now, and then these negative wave functions can overlap each other to result in the new sigma bond. So Psi2 molecular orbitals and supra-supra mode of interaction is allowed. Okay. So in the next class, we'll try to discuss about the stereochemistry involved in the Cope rearrangement reactions, and also possibly some examples regarding azacope and also oxycope type of rearrangement reactions. Thank you.